this is the rate of change of concrete as it's being poured to fill a concrete floor in a building. Okay, so let's move a little slow here, so I'll just do it manually. So what we have is time in seconds here. So the x-axis unit is time in seconds. Get used to my new writing pad here. So this is time in seconds, and then this is let's see, meters cubed per second, say, or foot cubed per second. Okay, so the concrete is being poured. This is the rate at which it's being poured at any time since the start of the pour. So I want to know, how much concrete do I have at x seconds? So this is also seconds here. And I want to write a function that gives me how much concrete has been poured. So before we write that function, what in general would this graph look like? What in general will this graph look like? Will it go up and down like that?
No, it would be like always increasing, but at varying rates. Yeah.
Okay, so someone has suggested that this will be an always increasing function. Agree with that?
Yes.
Yeah, so here, look, notice, like here at 15 seconds, what is the rate of change? The rate of change at 15 seconds is about
30.
Yeah, it's about 30. And that's a positive rate, right? That means that for every second, for every, what? Every change in time, the amount of feet cubed added is, what? 30 times as much as that change in time. So it's still going up. It's just going up at a lessening rate. So it's going to go up, and it's going to be going up the fastest right around, what, 7 or 8? Around 8 seconds. So it's heading up more slowly at first, but then heading up fastest. Try that again. Used my new pen. Heading up the fastest, and then about 8 seconds, it starts slowing down. And then it's not going to go back down again. It's just going to kind of level, keep increasing, but at a slower and slower rate. So we expect something like that. Well, I want this function exactly. I want the accumulation of concrete. So if there was a final exam, this could be the one question on the final exam. Could you write the function for the accumulation of concrete here, given that this here, t to the fourth e to the t to the fourth e to the minus t over 2 is the rate of change? Would you ace the final exam right now? Could you write it? So who wants to show me what that would be?
Can you repeat the original function?
Here's the rate. You mean the rate function?
Yeah, I see it now. Thank you.
Right, 2 to the fourth e to the minus t over 2. So how would we write the accumulation function for the accumulation of concrete at x seconds?
The integral from a to x of r sub f of t dt.
All right, someone learned something. Awesome. So it's going to be the integral from, we're going from 0. So actually a is set at 0 here, so I'll do a. From a to x of, did you say r of f?
Yeah.
And then we need t dt, right? We need some different variable than x. Okay, so would you have passed the final? All right, this is something we did lots and lots and lots. It's super important given you know how fast something is changing at every moment. We know how fast the concrete's being poured at every moment. We want to know how much of it we have at every moment. That was our net accumulation function, right? And so if I turn that on, see here. There it is. And graph. There we go. So that's what we predicted, something like that. Okay, so now I want to do something new. So we predicted what that accumulation function would look like. We sketched it, and then we know that integral gives us accumulation, knowing what the rate is. So I put that in and I graphed it. So now I want to try something new here. That's here. So here are those two graphs. Here's the rate of change. I guess I said seconds, minutes. It says minutes on this graph, and meters cubed per minute. All right, we're going with feet cubed per second, but regardless. And so what I want to do now is I want to graph. Let's stick with seconds. Seconds. And foot cube per second. And what would the units on this axis be? What would the units on my amounts of concrete?
Feet cubed.
Just feet cubed, right? Okay, and so what I want to do down here is I want to create a graph of given the, what is this? Given the amount of concrete, poured, at any amount of concrete poured, what was the rate at that amount of concrete poured? And I want to come up with this graph. Okay, so this is, so given the accumulated amount, what was the corresponding rate at that accumulated amount? So how can I do this? I have this graph here. How can I come up with the graph of rate as a function of how much has been, the accumulated amount that's been poured?
Could you use parametrics?
I don't know what that is. I want to, so I'm just, you know, I just want to take the information I have from these graphs and construct a graph.
So y is going to be equal to the rate of change over time, and x is going to be equal to the total amount over time.
That's right. So how can I figure out how can I get some kind of sketch of this graph? Anybody know how we might be able to do that? So when I have a graph like this, okay, whatever it is.
Would using antiderivatives help? Or normal derivatives?
Well, maybe, but I'm not going to deal with the functions. I just want to get the information from the graphs. So when I have a graph like this, what does that consist of? What is that graph? What are you looking at when you look at a graph? Is it a wire that we bend and kind of stick it on some axes?
A collection of points.
Okay, right. So what you're really seeing is a gazillion points, right? So the graph representation of a function is really a set of points, and each point shows a particular correspondence of the two quantities that we have. So this point right here would be what? It would be some amount and the corresponding rate. So if I want to get a sketch of this graph, what am I really saying? I want to get points. I want to get points of correspondence of rate and amount. How can I use these graphs to do that? How can I get 1 point? So I just want to get 1 point on this graph down below. So I need a correspondence of an amount and a corresponding rate. I just want to get 1 point. How can I do it?
If you want 1 point, you could just choose an accumulation
on the right graph and then look for that corresponding like time that goes with that accumulated amount of volume, and then look to the left graph and look at that same time and find the rate at there, and then just make 1 point out of it.
Okay, so what I hear you saying is pick a time. 7. And now I can use the graph to get the correspondence of amounts and rate at t equals 7. So there's the point for t equals 7 for the amount. Here's the point for t equals 7 for the rate. And so what's my amount? Say this is what, 200. So it's 7 seconds. We poured 200 feet cubed of concrete. At t equals 7, what was the rate? About, is that 70?
Yeah.
Okay, so what point do I have down here?
270.
270. So that would be a point. So at t equals 7, that gives me a correspondence point on this new graph where when 200 feet cubed have been poured. Oh, I kind of missed there. I think I got it now. I think it's that one. Yeah. So the rate of change at the amount 200 was 70 feet cubed per second. Does that make sense to everybody?
Professor, is that 270 or 290?
Does this say 80 here? Yeah, 90. Thank you. I saw 72 and then some other students. So
I think it is 70.
oh, jeez.
It's between 60 and 80.
Yeah, so it is 70. Okay. Yeah. Yeah, so this is 20, 40, 60, 80. So yeah.
But in the lower graph, you graphed it at 90.
Oh, I see. Is it right here?
Yeah, that's it.
I believe so.
Thank you. Thanks for speaking up. Okay. So 270. Does the idea make sense? So what could we do? So I want to get a picture of this graph. So what would I do to get an idea of what this graph is then? Because that's just 1 point. I have no idea what the graph looks like. I have one correspondence point. So what could I do?
Do a couple more?
Yeah, or a lot more, right? So yeah, at least a couple more. The more, the better, right? So let's take a look. So here's t equals 5. So t equals 5. Get the rate at t equals 5. Get the amount at t equals 5. And we're going to put the amount on the x-axis, the rate on the y, and that gives us a point. Okay, t equals 7, the one we already did. And we came up with about 270. So there's 270. T equals 9. Same thing. We're going to, for t equals 9, we're going to pull off the rate. We're going to pull off the amount. We're going to put the amount on the x-axis. And we're going to put the rate on the y-axis. Same thing now. T equals 11. Got the amount on the horizontal. The rate, the corresponding rate is the vertical coordinate. So we get that ordered pair. Oh, here we go. A little bit faster here. Here's t equals 13. There's the amount for 13. There's the rate for 13. Gives us a correspondence point. And so then we can get an idea of what this function is. So now there's 5 points. Gives us an idea of what this function is like. And we also have the point at time 0, we have 0, 0. So we have this point here. So it's going to be something like this, right? Something like this. That as the amount, so this makes sense, right? Because as time goes by, the amount just keeps going up. So as the amount goes up, the rate's going to increase. There's going to be a maximum rate. We saw that here. And then the rate's going to decrease. It's just now it's not a function of time, but a function of amount. The rate of change is a function of amount. Okay, so that's just getting some discrete points. So we could get a lot more here, right? A table of values for every t value. We could get the volume and the rate of change and plot them. So here's even a better view of that. But then eventually, we want to see this continuously, right? As t increases, we get a string of points of correspondence of amount, which is the blue vertical here, and rate, which is the red vertical here. So do it again. So as t increases, every time gives an amount, a volume, and a rate for which we plot a point. But then if we let time increase continuously, the string of points will generate continuously, and we'll get the whole graph. Okay, so does the idea make sense here? So in this process, so this is kind of a new kind of function, and we know function has an independent entity and a dependent entity. So in this process, what was our independent entity? And
The volume.
So I'm not talking about this graph. I'm not talking about just isolating this graph. I'm talking about looking at this process that we did to create this graph. What did we start with? What was our independent thing?
Time.
Yeah, time and seconds. I think seconds and feet cubed is more realistic here. It's not going to take 25 minutes to pour this much concrete. So this is seconds, and then feet cubed per second. And feet cubed down here. All right, so our independent thing or entity was time and seconds. And then what was our dependent thing?
Volume and rate.
Okay, notice he said two quantities, right? So for every time we picked, instead of getting just the single value of one quantity, we got an ordered pair. So volume and rate. So this is a new kind of function, right? This is a new kind of function. And this is the graph. So this is the graph of this function. But notice what's not shown in this graph.
Time.
Time doesn't have an axis. So your independent thing, in this case time, is behind the scenes. It's not graphed. What do we graph? We graph the correspondence of the two dependent variables. So I'm graphing the one dependent variable on the y-axis, x-axis, and the other dependent variable on the y-axis. So we have r sub f of t and f of t, and we're gonna graph those ordered pairs, but we don't have a t-axis, right? For every given point, there's a sum t that got us that point, that got us the value of the rate and the value of the volume. So this new kind of function where you have a behind the scenes variable, and then that's generating more than one quantity, and we're going to graph the correspondence of those quantities, both the dependent variables. We're going to graph those with the independent staying kind of behind the scenes, or kind of a little bit hidden. So this is the idea of a parametric function, someone said earlier. And normally we use, so for the independent thing is called the parameter. And conventionally we use t. Not always, but t is the convention for your parameter. The conventional value is t. So values of t are now not generating just the value of one variable, but the value of more than one variable, and we're going to plot the correspondence of those dependent variables. Okay, does it make sense? What just the general idea of a parametric function?
So, if we were given a parametric function, would we be told what the independent is? How would we ever know what the independent is?
It's the independent variable of your two.
Oh, okay.
Yeah, I mean these are each individual functions that you're used to, and so the independent variable of each of these is going to be the parameter. Okay, so let's graph this on GC. So I've got a file started here. So here are those two functions. And so to graph a parametric function in GC, you're going to use control 2. So control 2 sets up kind of an ordered pair vertically. So normally when you write, you'll write horizontally. You won't write vertically, but in GC, it's arranged vertically. And so I'm going to say equals. I'm going to hit control 2 again. And so what does x equal in our graph? So I want to graph the parametric relation of rate and volume. What was x? What was the x or the horizontal coordinate?
Volume.
Time.
Okay, so I got time and volume. So is it going to be in our parametric function? Oh, I did this wrong. Sorry. Did anyone catch that? Speak up. This is not right, right? What is this? What should this be?
Should be volume.
Yeah, we put volume, right? We put volume on the horizontal axis, and we put rate on the vertical axis. So that was my mistake. So that's what we're going to do here. We want to put volume. So we want F, and remember you need control 9 for functions. F of t on the x-axis, right? And then we wanted the rate on the y-axis. So this is telling graph all the points such that the x-coordinate is volume and the y-coordinate is rate. And so lowercase t is a built-in, it's a reserved symbol on GC for the parameter in a parametric function. So it follows this convention as well. So lowercase t will always it'll say, oh, you want to do a parametric function. So it knows that. Okay, and so then we graph that. And here's what I got. So what happened? Can you see that? Was that what we were expecting? For the graph of the rate as a rate versus the volume? What's going on there?
It's taking its own sweet time.
No, it's done. It is actually done. This is the, yeah, it didn't have any problem doing that. It just, we expected kind of a, we expected a whole hill here, right? Like a kind of a hill. Why did we only get that much of it? So the answer is over here. Notice what this says. As soon as we use that variable t, it pulls up this little thing over here. Can you read that? And what is that saying? It's saying that t is
0 to 1.
From 0 to 1. And what kind of time frame did we have for our function? It was a lot more than 1 second, right? Does anyone remember what the whole time frame was?
30, right? 30?
15.
Let's try, so I think it was, yeah, let's try 15, if I remember right. Okay, so I just changed it from t equals 0 to 15. Maybe that's not enough. Let's see. I'm zooming out. I need to zoom out on the x-axis. Oh, there we go. So almost, we could do 20. There we go. So now I'm showing t from 0 to 20, and it's going to give me all the points for the t values starting at 0 and going to 20. Okay, but suppose I wanted to graph more than one parametric function on the same graph, and they all had different ranges of t that I wanted to show the graph for. So an important technique is that we want to leave it at t equals 0 to 1. What happened? Okay, so now you can't see it because I'm zoomed out. I want to leave it at t equals 0 to 1, but I want to kind of adjust my function, my parametric function, to show the whole graph. So that if I had other functions that I was showing, you know, they might all have different ranges of t that make sense. Okay, and so then but I only get one range of t when I'm graphing on the same axes. So how can I adjust this now? So this thing is called the argument. What goes in? What goes into a function, the whole expression, what goes into a function is called the argument. And so we want, as t goes from 0 to 1, we want the argument to do what?
Could you just do f of 20t?
So we need the argument to do what? So we want the argument to go from what to what as t goes from 0 to 1?
0 to 25?
Yeah, sure. I had 20, but 25 is fine. So as t is changing from 0 to 1, we need what's inside the parentheses here to change from 0 to 25. And someone had a good suggestion. Someone said, what should we do? So what I'm going to make an expression in there so that as t varies from 0 to 1, what's inside the parentheses will vary from 0 to 25.
Could we do 0, comma 25?
No, we just need one quantity. You can't put a comma in there.
25
Multiply the argument by 25.
Yeah, so we do. No, we're not multiplying the argument. We're multiplying t by 25. Now the argument.
Oh, we're changing the argument.
Yeah, we're changing the argument, right? So now the argument becomes 25t. So does it work? When t equals 0, what do we get? 0.
0.
And then when t increases up to 1, this is going to increase up to what?
5.
25, right? So this works. When t is 0, we get 0. When t is 1, we get 25. And that would have the same effect as changing t from 0 to 25 if it were just t in there. So now if I graph it, I get the whole graph. Does that make sense? So this allows us to keep that range at t from 0 to 1 and graph other things that might have their range be in a different value of t. Okay. Any questions on that? So the idea of parametric function. What's the idea? There's this parameter. The parameter serves as our independent entity of the function, and it's generating more than one, a value of more than one quantity. In this case, we have 2, right? So this case, but it could be more. It could be 3 or 4. But in this case, we just have the 2. So values of the parameter are generating one value of one function that we're going to plot on the horizontal axis. Values of the parameter are generating values of another function, which we're going to have on the vertical axis. And we're going to plot ordered pairs. So we're going to plot ordered pairs of the 2 dependent quantities, which becomes our kind of dependent entity of the function. And we don't have a axis for the parameter. Okay, does it make sense? Okay, well, so this opens up the possibility for lots and lots of graphs of lots and lots of curves that maybe we haven't seen before, or haven't seen anything like before. So for instance, something like this. So you can see the t value up here. So now t is 3 right now, and now t is 3.5 right now, and then it's going to start over at t. This t equals 0, this t equals 1 right there. Okay, so my question to you is this the graph of a function? Is this the graph of a function?
Yes,
She says yes. Why?
because it's still constructing the points as our independent variable increases.
But
Okay.
isn't it breaking the vertical line test?
No, because for every independent value, we're not seeing the independent value, we're only seeing the outputs. But
Okay.
for every independent value, there would have been one dependent output. We're just seeing only the dependence.
Okay, so
All right.
what she's saying is, given any value of t, right now, what's the value of t?
3.52.
Yeah. Okay, right now the value of t is 3.52. For that value of 3.52, do I get one result, exactly one result, or more than one result in terms of the kind of the dependent entity?
Just one.
Yeah. So now you just get you get two values, but of x and y. So this is say f of 3.52 and g of 3.52. So we don't have a context here anymore. We're just looking generically at plotting a graph. Okay, so it is a function if what though? So we have to really qualify that question, right? So when I said, is it a function, did some of you have the reaction, no, it's not? And that's okay? And what would the reasoning behind that be? How is it not a function?
The vertical line test again.
Okay, but so what is the vertical line test about? So that we want to understand what we mean by that. So, okay, it fails the vertical line test, but what's that? I mean, what's that about?
So whenever you put in a single independent value, you're only receiving one output for it, and it looks like here we're receiving 2 output.
All right, so here x is 0.3. When x is 0.3, there's 2 y values that you get, right? So is it a function or not? So a function is always about an independent thing, entity, quantity, and a dependent thing, entity, or quantity. So when I ask you, is it a function? It depends, right? It depends on what you're talking about. So how is it not a function? What is not a function here?
That we're getting 2 y values for 1 x value.
Y is not a function of x. Right. Given at least one value of x, but there are many, there's more than one y coming out. Right? This is a non-predictable situation. Functions are about predictability. Whenever you put a certain x value in, you always get the same y value back. Okay? But this isn't happening. So how is it a function? So y is not a function of x, but this still is the graph of a function. How can we see it as the graph of a function?
Could you just say that y is a function of t and x is also a function of t?
Okay, so put it all together. What is a function of t?
X and y?
Right. Ordered pairs, x, y, is a function of t. And so pairs of quantities taken together, the x and the y taken together, is a function of t. Why? Because given any t, given any value of t, so here's 3.52. Let's go back and do, here's 1.5, here's 1.5 down here. When I put 1.5 into this function, do I get a single ordered pair, or do I get more than one ordered pair?
Single ordered pair?
Yeah, I just get this ordered pair right here. This ordered pair xy. And that'll be true for every t. For every value of t, there's only going to be one point that that results from that t. So what about the fact that it crosses the origin? Is that a problem? Notice I'm getting 0, 0 many times. Is that a problem in terms of a function or not?
No, because you can have multiple output values for multiple instances of the independent variable having the same output variable.
Right. Is sine a function?
Yes.
Yes. Do I get the same output lots of times?
Yes.
Yes. That does not violate what we're talking about. The point is that given an x, there's only one y associated with it. You don't get more than one y for a given x. That's not to say that different values of x could give you the same y. That's perfectly fine. And that's what sine is like. Right? All these values of x are giving the same value of y. That does not violate this being a function. To be a function, it means that when you pick an x, you only get one result, y. And that's perfectly fine. Same thing's happening here. When you pick a t, do you only get one particular ordered pair associated with that value of t? And the answer is yes. You might get the same ordered pair for different values of t, and that's okay. But the problem would come is if you, for a value of t, for the same value of t, you got two different ordered pairs. Well, that never happens. Okay, does it make sense? All right, so we're gonna figure out what this parametric function is. So what do you notice about? Let's look at. What do you notice about the range of x and the range of y here? What does x? What's the span of x and the span of y?
They're both -1 to 1.
Right. So x is going from -1 to 1. So is y. And it's kind of repeating, right? So what does x do? X goes from 0, just looking at the x coordinate now, 0 to 1, back to 0. This is just the x-coordinate. Then to -1, and back to 0. So notice, when did x go from 0 to 1? So as t goes from, so t ranges from 0 to 4. So let's see, as t goes from 0 to 1, what does x do? So here's t going from 0 to 1. 0. Oops, I went too far. As t goes from 0 to 1, what did x do? X went from what to what?
0 to 1.
It also went from 0 to 1. Did you see that? So we just care about the x-coordinate. So I showed you t going from 0 to 1, and we got the x-coordinates from 0 to 1. Okay, now as t goes from 1 to 2, what does x do?
1 to 0.
So let's watch it. So here's t going from 1 to 2, and x is now returning back to 0, just the x-coordinate. You see that? Just the x-coordinate went from 1 back to 0. And then as t goes from 2 to 3, what does x do?
0 to -1.
0 to -1. Let me show you that. I'll just show it all at once here. So here's t going from 2 to 3. X is going from 0 to -1. Does everyone see that? And then as t goes from 3 to 4, x goes from
-1 back to 0.
-1 back to 0. So what? Look, so let's kind of graph just the x function as a function of t and see if we can figure out what this is. So 1, 2, 3, 4. As t went from 0 to 1, x went from 0 to 1. As t went from 1 to 2, x went from 1 back to 0. As t went from 2 to 3, x went from 0 to -1. And then as x went from 3 to 4, sorry, t went from 3 to 4, x went from -1 back to 0. So I'm putting x on the vertical axis here. Anybody recognize that?
Is it sine?
Yeah, it looks like it could be sine, right? So we're not confident in, it's not a proof in between, but it sure looks like it could be sine. But then we have an argument issue here, right? So for the sine graph, what is that right there? What's half of a cycle of sine? What would t be?
Is it pi?
It's pi. A full cycle is 2 pi. So we think that x could be a sine function, but we need the argument of sine to work out so that what? So that as t goes from 0 to 1, x goes from what? 0 to actually goes to 0 to pi over 2. Or x needs to go from, x needs to go from 0 to 1. Okay, wait a sec. This is confusing. Sorry. Did not do that well. So the t value that we have 1, 2, 3, 4. Those are the t values, okay? But normally that's pi. And normally, for sine, that's pi over 2. Right? So as t goes from 0 to 1, we need the argument to go from 0 to pi over 2. Right? We need the argument to go from 0 to pi over 2 so that we get this first quarter of the sine curve. And as we go from 0, as t goes from 0 to 2, we need the argument to go from 0 to pi so that we do half of a cycle. So what will my argument be?
Pi halves t.
Pi halves t. So as t goes from 0 to 1, we go from 0 to pi over 2. as t goes from, say, 0 to pi, as t goes from 0 to 2, we're going to get pi. So it looks like it's right. And let's try the whole thing. When t reaches 4, what do we get inside here?
2 pi.
2 pi, and that's what we want, because at 4 we want to finish the cycle. So when t equals 4, we get 2 pi in there, and we finish the cycle. Okay, what about y? So that we just figured out what the x coordinate of these points are, and so that's the first half of our ordered pair. All right, what about y? So what does y do? As t goes from 0 to 1, watch what happens with y as t goes from 0 to 1. What did y do?
It went from 0 to 1, then back to 0.
Yeah,
again.
it went from 0 to 1 and back to 0. So let's just do the graph. So when t went from 0 to 1, y went up to 1 and back to 0. And then when t goes from 1 to 2, what's going to happen? Y is going to go, as t goes from 1 to 2, down to -1 and back to 0. So when we reach 2, so from 1 to 2, y is going to go down to -1 and then back to 2. So what is this function? Is this, first of all, sine or cosine?
Sine.
Sine. And so we need the argument, when t equals 1, we need the argument to be what?
Pi.
Half of the cycle, pi. And when t equals 2, we need the argument to be?
2 pi.
2 pi. So this one's easier. What's my argument? So that t equals 1 gives pi, t equals 2 gives 2 pi.
Pi.
Pi t.
Pi t. Let's take a look. What's up here? There it is. No, this one. All right, so this is what we said: sine of pi over 2t, sine of pi t. So that's what that's this parametric function. The x-coordinate is sine of pi over 2t, and the y-coordinate is sine of pi t. And that generates this kind of figure 8-ish graph.